Hello! In this video we're going to look at a specific example for finding eigenvalues and eigenvectors. We're going to use that example that we already checked out when we were constructing an alternate basis and looking for a reflection. So we want to find the eigenvalues and eigenvectors for the linear transformation which reflects vectors about the line y is equal to negative x. From another video, you may recall that this was t of x is equal to a times x, where a was 0, negative 1, negative 1, 0. So we find the eigenvalues by solving this equation. We want to find where the determinant of a minus lambda I is equal to 0. We're going to solve that for lambda. Here's our A, our standard matrix, and subtracting off this lambda I really results in subtracting off lambdas from the diagonal. Here's our setup. I have A minus lambda times I. These lambdas come into the diagonal, times 0 just leaves them there. I have 0 minus 1 lambda, negative 1 minus 0, negative 1 minus 0, and 0 minus lambda. I want to take the determinant of that, so I'm going to multiply down the diagonal, lambda squared, subtract up the off diagonal, subtract off negative 1 times negative 1, which is 1. I can factor that out, and I get lambda minus 1 times lambda plus 1 is equal to 0. That will give me eigenvalues of plus and minus 1. Now to find the corresponding eigenvectors. To find the corresponding eigenvectors, I'm going to find the non-zero null space of a minus lambda I for each lambda. Let's start with 1. When I take 1 and plug it back into that a minus lambda I, which is right here, I get negative 1, negative 1, negative 1, negative 1, and I augment that with 0. So this is easy enough to solve, but I'm going to use the calculator to sort of show you how you might do this. I have that matrix stored in A. I'm going to do a second matrix. I'm going to do an RREF, which we do a lot in this class, and go back to matrix and hit up A. So we should get a matrix here that has a free variable, because that will give us our non-zero null space. So our reduced row echelon form is 1, 1, 0, 0. I have 1, 1 augmented with 0, and 0, 0 augmented with 0. That means I would have, if I call this x1 and x2, I have x1 is equal to a negative x2, bringing this x2 over, and x2 is free. So a good eigenvector I can get from this, if I just factor out the negative x2, is going to be negative 1, 1. That will be my first eigenvector corresponding to 1. Remember, you can have any multiple of this, so that would work as well. Alright, now we'll find the one corresponding to negative 1, and that is stored in my matrix B, so I'm going to go back to second matrix, RREF, second matrix, B. For this one I get 1, negative 1, 0, 0. It may be obvious to you what your eigenvalues, vectors I should say, will be. And if it is, especially for these 2 by 2s, you can go ahead and solve them that way. In this case, I'll have x1, if I recycle these variables, is equal to positive x2, and x2 is free. Factoring out the x2, I'm left with 1, 1, but again, it could be any multiple of this vector, so it could be 2, 2, negative pi, you get the gist. So that's it. Therefore, what we have for lambda equal 1, we have this eigenvector 1, negative 1, or negative 1, 1. See, I even used a multiple down here. And this is called the eigenspace for A, associated with eigenvector, eigenvalue 1. And for negative 1, I have the vector 1, 1. So this is the eigenvalue and eigenvector associated with the eigenspace A, called E sub lambda equals negative 1. We're going to follow this example throughout and see how this will tie in with some more theory later. Hope this has helped. Thank you.